right, good morning, everyone. Hope you all are having a good day. So I'm going to be going over chapter 13 today. Just a reminder, we're going to be ending class probably 30, 40, 50 minutes early. We'll see. Want to make sure everyone has time to go to the career fair. Any appointments you may have set up, I think that's pretty important. All right, so it's all about data structures. We're talking about database storage architecture, file organization, organization of records and files, database buffer, and column-oriented storage. Okay? So first thing to talk about is file organization. Okay? And in file organization, what we're doing is we're thinking about how we're actually storing the database. Now, what's one of the good things about modern SQL? Literally one thing. Just name something beneficial about SQL. Okay? So the ease of use extends toward how we store the database contents, don't they? Okay, so it's pretty easy. So most of this stuff isn't stuff we have to worry about. However, if you're working with a large enough database, you may not want to stick to the defaults. Is that fair to say? So that's what this chapter is all about, is if you weren't going to stick to the defaults. So in general, we're going to store databases basically in several files. And most of the time, each table is going to have a file. Okay? Lots of different ways we can approach it. Not one right or wrong way. But we can think about the file as being just a collection or a sequence of various records that we have. So in a lot of cases, we may have a database that has millions of records. Okay? And then each of the records is basically just going to be the fields associated with it. So another term for record is what? Starts with an R. Okay, so not a log. What is a database record? Three letters, starts with R. Look it up. It's a row. Okay? So those are all the same term. All right? And in general, the way we approach this is we have different records that we're going to be using. Okay? And specifically, we're going to be assuming that each of the record sizes is fixed. Okay? We're also assuming that each of the columns is going to have only one type within it. Okay? And inside of a SQL database, that's a pretty fair assumption because when we define a column, okay, we have the column name followed by what immediately after it? Data type. That's exactly right. Okay? So with that assumption in mind, is it fair to say that if we're defining the data type for a particular column, that we can only put that particular data type within inside that column? I think that's a pretty fair assumption. Okay, and then finally, we're saying is that we have different relations. Another way to think about this is if we have different tables, they're going to be inside of different files. So basically, each table has a file. Now, don't get too caught up in this because tables can have multiple files. That is a possibility. We're going to talk about that in a couple slides. But the overall idea is that, in general, we're assuming, for right now, that a table belongs to one file, and a file belongs to one table. Is everyone with me so far? Okay, so we have two different types of record storage. We can do fixed length, or we can do variable length. Okay, so think back to the differences. So an example of fixed length is whenever we're storing a character. Okay, so when we specify char data type, and we say, someone throw me an integer. Okay, so between 0 and 1,000. Okay, so if we say the char is length 900, is that a fixed length or is that a variable length? Okay, that's a fixed. Okay, so don't get too caught up in all this stuff. You know, it's important to not overthink a database. You know, can you go very in depth with all this stuff? Absolutely. Okay, so really all we're doing here is we're just saying that we are storing things in a fixed length fashion. That doesn't mean that every single record of this char that has a 900 length, doesn't mean they all have to have 900, does it? It just means we're storing 900 characters regardless of whether or not that's needed. Is this a good approach? It can be, okay? So, for instance, if I said we're going to be storing state, all right? And we want to use the data type char 2. Does that approach make sense? Can you store every state with 2 characters? Okay? So at least United States, all 50 states have a 2-character abbreviation. Everyone agreed to that, right? At least everyone who had any ability to agree to it. Okay? That's all we're talking about with fixed length. So there's some advantages, okay? But in general, okay, what we're thinking about is just how we actually sort of manipulate records inside of this approach, okay? So basically what we're doing, we're deleting a record, we're basically just moving the other records, all right? And moving record in to I, okay? So those are 3 different ways to do it, basically. But the end goal is that you're deleting a record, okay? So we've established another term for record is row. All right, that's important, okay? A lot of this stuff today is not important. But if you go to a job interview and they ask you a database question, okay, they're not going to ask you about fixed length records. Not likely. They're going to ask you basic SQL manipulation, which we've done quite a bit of. Is that fair to say? Okay, we've done 2 pretty sizable labs. If you can do basic select statements, if you can do basic insert into, you're in a really good spot. Okay, so the end result here is that we're deleting the record. All right, in contrast, we have variable length. Okay, so variable length, what we're doing is we're storing something that's not a predetermined size. Okay, can varchar go up beyond 200,000 characters? Yeah. Does it most of the time go beyond 200,000 characters? Definitely not. But if we don't specify a max size for a varchar, the max size is the max size of varchar, which if I'm not mistaken is 255,000. It's pretty close to that if that's not the exact max. Okay, that's pretty large. What happens if we have something that large that we want to put in a database? What are we going to do? Is that going to be fast to process? It's going to be incredibly slow. All right? You could make an argument about whether or not that even belongs in a database at all. And, in a lot of cases, it probably wouldn't have to. One of the big deciding factors is how are you going to use it? Okay, so if you're going to be collecting it, and if you're going to be having thousands, maybe even millions, you may need to be treating that a little bit differently. That may be something that goes in a database. Now, if you have something that's just a one-off, are you going to want to make a table to stick 200,000 characters in? That's hundreds of pages of text, by the way. All right? votes yes? Who votes no? Are you going to make a special table for one single 200,000 characters? You know, I would probably lean more towards it doesn't make sense to put it inside of a table. However, you could, and it's going to be context specific. Okay, so basically what we're doing here is we're just storing the record in multiple files. Okay, specifically, I would say you're storing each in their own file. Okay, because if you have something that large, you know, you're going to face the possibility of corruption. All right? The larger something is, the more likely it is to be corrupt. Is that correct? It's correct. Okay, so you definitely want to keep that in mind. Also, another advantage is sticking things in multiple files, which, by the way, a lot of this will be handled automatically. Okay, but for processing, what did I say the general rule of thumb is for RAM in a database? You need X amount of RAM for every Y gigabyte of your database. So 2 gigabytes for every 1 gigabyte. That's exactly right. Okay? And that's going to allow you to have some room for overhead and for other tasks to take place. But a lot of databases exceed a terabyte. All right? You know, 2 terabytes of ECC is not cheap, is it? So it's not always going to be practical to follow that rule, is it? Okay, and beyond that, there does get to a point to where if you can store an entire database in RAM and have a terabyte left over, that's probably a little bit more than you need, is it not? Okay, it probably is, especially on a server. Because with servers, we obviously control the background tasks pretty effectively. Think back to what we did with Windows Server. Okay, you guys remember what we did? We controlled the server's task that it was doing. All right? So that's something you're going to be doing. And, you know, what you're thinking about is the record types, okay, it's just a varchar. All right? And there's other types as well. We're going to cover those in the next few slides, like blobs and clobs. But the idea is that a lot of what we've done inside of databases have been fixed length. That has some advantages. Obviously, there's some other times where you'd want to use a variable length. I don't think I need to spend all day talking about that. Okay? So with anything in a database, there's going to be an inherent order. Okay, and that order is most likely going to come from one of 2 places. The first would be an index. We're covering index in the next couple classes. Basically, just understand something that's going to allow us to make processing faster and more efficient. Second place is going to be the order in which the data were input. So those 2 things what we're talking about when we're referring to order within inside of a database. Okay? So again, think about fixed length. Okay? That has a very fixed length associated with it. Okay? That's not always going to be what we're going to use. Okay? But basically, this is what we're going to see if we were using variable length. The advantage is that we can insert whatever we want, basically wherever we want, without regard for are we following a predetermined structure. All right? So storing large objects, larger than a 200,000 character varchar. It's very possible we may use the blob or the clob data type. All right? Binary large object. So with these, what we're basically doing is we're assuming it's going to be smaller than a page. Now, does that page mean 8.5 by 11? Definitely not, okay? Because we can definitely consider the page is a relative size here, all right? So some different ways to do this, okay? Store the file in a traditional file system. All right, so think about if you had an enterprise. All right, what type of appliance do you probably have on your network? So I'm not talking about a small business, I'm talking about an enterprise. 3 letters starts with S. We talked about this last semester in networking class. SAN. Okay, exactly right. So that's basically saying you could store it on a SAN. And I think that for most large objects, I think you probably will. All right? Doesn't make a whole lot of sense to store objects in a database in a lot of cases. I'm not talking about doesn't make sense to store data. I'm talking about straight up a big object, multiple gigabytes. It's going to be highly inefficient. And what do you need it for in a database anyway? You probably don't. Okay? So you can store them as files. Okay, so instead of storing the actual binary large object, what you're doing is you're basically storing a reference to the file that the large object is stored in. So I'll give you an example of this. All right, I use an application called Mendeley. All right, so what Mendeley does is it basically it doesn't actually store the PDFs, but it stores a link to PDFs. Okay, so let's pull this up and show this briefly. Okay, so this is what it looks like. This is an example of an application that would store links to other files. Okay, and you can see that if I were to open up one of these files, okay, it would open it up, but this is basically a database that does that. All right, does that make sense? It's another way to store large objects. Okay, and then finally, break it into small pieces and then store the tuples in different locations. Now, to me, this one makes the least sense. Okay, but this could be done, and depending on the file structure, it may make sense. But in general, I think that just storing it on a traditional file system probably makes the most sense. All right, does anyone disagree? It's okay if you do. So organization of records and files, some different terms to know. All right, first, we have heap. Okay, heap can be placed anywhere we say. So if I had a database, I can plop it anywhere that I want. All right, and sequential, okay, the name sequential implies what? Sequence, in order, exactly. Okay, and that order is going to be determined by the search key, which again, we're going to be doing indices, I think next class. All right, multi-table clustering. So what we're doing here is we're basically taking multiple tables, okay, and we're just allowing them to be stored within inside of a single file. So go back to this example here. See how we had one table stored in multiple files? And we said that we were going to have one table we're not going to have two tables in the same file. Well, with multi-table clustering, we are going to have them in the same file. It's not an approach that I think is particularly useful, because most of the time what speeds up processing is actually breaking things up, not combining them. And with organization, it doesn't really buy you any advantages. However, that's what it's called. Does that make sense? Okay, and then finally, hashing is going to be where instead of using the search key itself, okay, you compute a hash of the search key, and you use that. Now, the obvious downside is, what about a collision? Well, that's going to cause some problems, all right? But the upsides are, if you have a particularly large index, then that index can be greatly shortened by using a hash of it. All right, does that make sense? Now, the good news is that collisions are rare. They're not unheard of by any stretch. You're going to run into them, but it's less than 1 in a million, especially for the more advanced algorithms like SHA-512 or I guess SHA-3, those sort of things. Okay, so sequential file organization. Again, we have to go through this sequentially. So one advantage of this, or one disadvantage rather, is if you're wanting to do, say, a subset of the data, if it's sequentially organized, you're going to have to go through everything and then pull out what you don't want. So that's a pretty big disadvantage, is it not? All right, so basically you're just ordering them by the index, which the index is going to be in this column here. And basically you have your different records. All right, that's all we're doing with sequential. Okay, so if you want to delete something inside of a sequence, use a pointer chain. All right, now the good news is that if you're deleting something that's using sequential file organization, do you have to know what a pointer chain is to delete it? No, you don't. Okay, why not? Why don't you have to know? Well, I mean, you can always get rid of a table, but I'm saying, you know, from a user perspective, if I wanted to remove a record, okay, I can do that with delete. It's not a problem. Do I have to know what's going on in the background to do that deletion? No, you don't. So I wouldn't even worry too much about this. All right? But basically, what you're doing when you're inserting is, if there's free space, it's going to insert at that free space. Okay, if there's not free space, then what it's going to do is it's going to put that inside of an overflow block, which again, all this process, deletion and insertion, it happens automatically. All right, but this is the theory behind it, in case you wanted to change for whatever reason. Okay, but it uses a pointer chain. The pointer chain is what ties the record to the storage, basically. All right, so there's a lot of disadvantages to it. Another thing is that, you know, as you're inserting and deleting over time, stuff's going to get out of order. Okay, because if there's free space, what does it do if you're inserting? So if you have free space and you're inserting a new record, what does it do? So it does update the pointer chain, and it's going to insert it at that free space. That free space may or may not be where you'd want the record to be from a sequential perspective. Okay? So what has to happen is that it's going to, over time, it's going to reorganize the records. Okay, it's kind of like defragmenting a hard drive. All right? So if you have a mechanical disk, this is the same type of process. Okay, so the idea behind defragmentation is you want to get the like data on a similar location so it can be read more quickly. Is that right? Exactly what happens. Okay, it's just a little bit different, where it's less about where it's stored physically, and it's more about how it is organized from that perspective. Okay, so this reorganization takes a lot of processing power. All right, I mean a lot. Because basically what you're doing is you're constantly grabbing records, updating pointer chains, and reorganizing stuff, rewriting. None of that's very fast, is it? I mean, so it's relatively fast compared to doing it manually, certainly, but you know, this is just a slow process. All right, and that ultimately will restore sequential order. All right. So you can see here, what it's doing is inserting this new record here. And you can tell it's going to insert it into the place that it really shouldn't go. All right, so that has to be reorganized. Okay, partitioning. This is a really important concept because I could conceivably see where you may not be able to fit an entire database on a single disk. That's something that you're going to come across if you happen to become a database administrator of some sort. Okay, so what happens when you partition a disk? So yeah, I mean, basically, you have a disk, and let's say it's a terabyte. Okay, so by default, it probably is going to have a couple partitions, but for the most part, one of the partitions is going to be almost the entire disk. All right? And from a home use perspective, there are very few reasons to repartition that. Now, from an enterprise perspective, what if I want to give one user half of it and another user the other half? How do I do it? I partition it, right? Same exact process with a database. All you're doing is you're taking the database, you're splitting it to where it can be stored separately. All right, so one example. Let's say you had a transaction table, and your company has a lot of transactions. Okay, so if they have a lot of transactions, what does that mean about the size of the transaction table? It's going to be very large. So you could split it up by whatever characteristic you wanted. All right, so the book used the example of splitting it by year. Could you split it by the year and the month if you needed to? Okay, let's say we are Uber. All right, does Uber have a large number of transactions? Very large. Do they collect a large amount of data about each transaction? A ton. It's not just the customer ID and the right amount. A huge amount of data for a single transaction. Imagine having millions of transactions a month. Now, Uber doesn't actually use SQL databases. All right, because for them, when you're adding that much data consistently, all the overhead from SQL is quite taxing. And what's another consideration for Uber? Okay, are they focused on differentiation, or are they focused on low-cost leadership? Okay, are they cheaper or more expensive than Lyft in most cases? They're cheaper. Are they cheaper or more expensive than traditional taxi cabs in most cases? Much cheaper. Okay, so they're probably going to be a cost leadership firm. Is that fair to say? So with that said, they're focused on reducing the cost. Okay, one way to reduce the cost, if you're having to have a large amount of computational power, is figure out ways to not have so much computational power. And that's exactly why Uber transitioned away from relational data storage, okay, because it was too costly. Non-relational storage was much less costly for the processing they are doing, okay? And again, that's true for them because of the amount of data. For most companies, even a lot of Fortune 500s, that's not going to be true at all, all right? Does that make sense? It's not to say that it wouldn't be less processing. It's just you're talking about such small amounts of difference for most use cases that the ease of use for relational data models is going to be far exceeding the drawbacks. Does that make sense? So for every single one of your projects, all right, which I think there are 3 groups, or is that right? Okay. All you're going to use a relational model. Okay. You're not going to be using non-relational. So basically, what you can do is you're going to define the range using either where or using having. Okay, either of those approaches are going to allow you to select the specific range of data that you need. It's going to be particularly usable for things like if you, for whatever reason, all right, and in 2022, I'm not sure why this would be the case. Just going to preface it by saying that. But if you need to save money and you want to store the longer term stuff on a slower medium like a magnetic drive or even a tape drive, okay, you can certainly do that quite easily. And you can store the current year on solid state media. All right, and I would probably say that it makes more sense to store the current year on something like a RAM disk and then have a non-volatile backup of that RAM disk and then have the older years on an SSD. That just makes a lot more sense for 2022 in my opinion. All right, I'm not the only person with an opinion though. Okay, let's face it, per gigabyte, magnetic drives are still cheaper, aren't they? They are. Quite a bit. Okay, you can get a 14, even 20 terabyte, magnetic drive for certainly a lot less than you could get a 4 terabyte solid state drive. All right, but those prices are starting to converge. They have been for some time. All right. I've seen 2 terabyte NVMe drives for as little as $140. All right. That's getting pretty cheap per terabyte, isn't it? It's not bad at all. Okay. So you certainly want to consider those things. All right. Like I say, I wouldn't suggest sticking anything on a magnetic disk. But magnetic disks do have some advantages, especially for enterprise environments. Talked about the cost per gigabyte. That's obviously a big one. Now, the overall operational cost is probably going to be higher, okay, because you're having more heat, which means you have to cool the heat or exhaust the heat, which takes additional electricity, obviously. Electricity, obviously, is an expense. And then, of course, you also have the consideration of noise. Not necessarily a huge thing, but you may end up exceeding the OSHA limit. You may have to provide what are those things called? Ear protection? I don't remember. There's a term for them. You guys know what I'm talking about, the little foam you stick in your ear. Earplug, that's it, thank you. Okay? You may have to provide earplugs. That's an expense. It's not a huge expense, but it's an expense nonetheless. Some other disadvantages, we talked about heat, talked about power differences. We didn't talk about the power of the drive itself. We talked about power from the perspective of you have to cool the heat. Okay, so if you have the drive running itself, you're going to be using about 10 times as much for the same operations. Is that right? It's going to vary quite a bit by drive, but in general, you know, if you're spinning something around and storing it magnetically with an electromagnet and other types of magnets, that's not an inexpensive way to store data. All right, so you definitely want to consider that. Okay, but depending on how your data is structured, using partitioning may possibly save you some resources when it comes to stuff like how do we actually process, because if using where having to specify the year, if that's how the data is partitioned, then instead of using a database that may have 10 or 20 years, using a database that has 1 year. Okay, that's going to save on operations. Does that make sense? So again, if you were using where or having and you didn't have the data partitioned, you would still have to look through the entire data. Does that make sense? All right, data dictionary. It's going to be broken down by table. You're going to be storing information about each column. Okay, you're going to define the column. You're going to say what its data type is, and you're going to give an example of it. That's all a data dictionary is. Okay, what's the purpose behind a data dictionary? Why should we bother to do them? Why do we document anything, for that matter? Okay, so you want to make sure you can keep track of it. And let's face it, you know, who stays at a company forever? I don't mean for 30 or 40 years. I mean forever. Can you think of anyone in history who has run a company forever? One person. You can't, can you? All right, why not? People die. All right, people leave a company. Those are the two main reasons, actually. Probably the only two reasons. You either don't continue employment or you pass away. All right? So either of those two things mean you have to document. So that way, when different people come in, they can refer to the documentation. All right, what happens if you don't document things in an IT environment? Lots of confusion, exactly right. Okay, so it means you have to spend a lot more resources on training than if you just put aside a couple hours a week to document anything that's needed. All right, so documentation is vital no matter what you're talking about in IT. This is how you do it in a database. You just make a data dictionary. But you know, there's going to be a lot more that goes into a data dictionary as well. You're going to have stuff like the relations. How do we define the relations? What are the primary and foreign keys? So again, that's all going to be found in the definitions and data type column. Okay, because you're saying what specifically are we going to use to link the records between tables? You have to have something in common, all right? So if I were to draw an employee table, and if I were to draw a department table, what would be a good foreign key to use for that? If we assume that employee belongs to one and only one department, department has one-to-many employees, what would be a good foreign key to use? Okay. So what's the downside with using that? Okay. Could we face an anomaly? Okay, so specifically a deletion anomaly. Let's say that an employee changes department. Is it possible we may need to know what department they belong to? Okay, that's possible. So we could use department ID inside of employee. If we're assuming that they have one and only one department. All right. You know what a sneakier answer may be? What if we said foreign key boss? Okay, that doesn't tell us who belongs to which department, does it? But it still is a foreign key on one side of the relationship. All right, so realistically, I think that putting department ID on employee probably makes a lot more sense. That was your suggestion, right, Ben? Makes a lot more sense. Now, say we wanted to have a proof, or not proof, let's say we wanted to have a way to avoid a deletion anomaly. What could we do instead? Think about how we address the deletion anomaly with something like pay. What do we do for that? We didn't put pay in employee. Where did we put it? Associative entity. So is it fair to say that we may have an associative entity between employee and department? Okay, and then we would put the department, and what else would we put inside of that associative entity? So we'd have employee ID, department ID, what else? We could put position, start date and end date. Exactly right, because that way, let's say someone changes department. It's not exactly unheard of, is it? We know when they were working for a particular department. That's all we're talking about here. Does that make sense? All right, let's talk about storage access. Okay, so basically what we're thinking about is we have blocks of data, and that's just a unit that we're going to be talking about. And what we're trying to do with a lot of relational models is we're trying to minimize any sort of processing, any sort of storage modification, and specifically any type of block transfer, okay? So some ways we can do that. Okay, when we're processing, we stick what we're processing inside of a buffer, okay? And that buffer is going to allow us to have probably some really fast way to access, maybe to perform whatever operations we need, okay? And this is all going to be handled by a buffer manager. Okay, so buffer manager determines what goes in and out of a buffer, all right? Some different types of buffers, okay? Caches, RAM, sometimes different types of RAM, like VRAM, NVRAM, those sorts of things could be used for a buffer. All right. So again, the buffer manager is going to be what is actually controlling what goes in and out of a buffer. All right. So we can use non-volatile storage to, of course, be able to write stuff for longer-term use than volatile storage. Things like NVRAM, okay, non-volatile random access memory. That's certainly one approach we could take. Okay. What we want to do So we want to avoid performing writes to the main storage medium. Okay, and the obvious reason for that is because it's probably going to be slower. Is it not? Let's say you have a system with NVMe. Okay, that's its main storage medium. Is NVMe faster or slower than DDR4? NVMe is much slower. It's still fast compared to traditional solid-state drive on SATA interface, isn't it? You know, depending on the drive, you may see it be anywhere from 4 to, I've seen NVMe go up to, I think, 5 gigabits a second now. Or not 5 gigabits a second, 5 gigabytes a second. Okay, because let's face it, the SATA can hit 6 gigabits a second. All right. DDR4 is a lot faster, though. Okay. Especially when you start getting into the higher clocked DDR modules. Okay. So, you know, that's certainly going to be a consideration. All right. So what you may also use is a log disk. Okay, so the log disk's entire purpose is to collect what you're changing. So it's going to basically form a log of your updates. Not the actual updates themselves, just a record that they occurred. Okay, so with a log, it's going to be stored sequentially. Okay, because what's a big component of any log ever? Okay, any system log ever. Not like a log you go cut down. What's a big component? Date and time. So that implies sequential, does it not? So you're not having to seek to figure out where it can be put. You're just putting it at the end. So that's going to be a lot faster for writing to it. Okay, and basically, if you have that on a separate disk, that's going to speed up processing and updating. All right. You can also use journaling file systems. All right. This is particularly used in a lot of Linux and Unix systems. All right. Who uses a Mac in here? Okay, a couple people. Do you use the journaled file system on Mac? You probably do, especially for your main boot drive. All right. So what that's doing, okay, just another way to do things. Can be faster depending on what you're doing. All right. Now, if you're not journaling, okay, it's very possible that you could have corruption occur. Okay, because that journaling, it is overhead, but it reduces that risk of corruption whenever you're performing any updates. All right, talk about column-oriented storage. It's a fancy way of saying that instead of having a table have a file, the column has the file. That's all there is to it. Okay, so you can see here, we're basically storing each of the different columns inside of their own file. All right, so we have this column, this column, this column, and this column. And you see how they're all different, they're not touching each other? That's the book's way of illustrating they're in different files. All right, so we're going to call this columnar representation. All right. So some benefits. All right. If you're only addressing a single column, you can have reduced input and output cycles, which reduce the overall processing power needed for your database. All right. You can, of course, also, because you're not storing an entire table, you're just storing a column, it's more likely that that could fit inside of a cache file, particularly what you're currently working on. I'm not saying that's a huge advantage. All right. I'm not going to lie to you. All right. But depending on what you're doing, it may make sense. So the idea is that you're not storing an entire column inside of a CPU cache, but you're storing what you're actively working on. You're just more likely to be able to do that. All right? And both of those things are going to lead to faster processing, obviously. All right? Faster processing is a good thing. All right? But there's a lot of drawbacks, because basically what you're doing, you know, that's definitely not the default. Okay, so if it's not the default, it means you have to configure the data to that way. That takes not only time to do the configuration for, which labor is not free, is it? Okay, so that's going to be pretty labor intensive right there. But the actual deconstruction of the individual tuples, okay, that's not going to be very efficient. All right? So then anytime you have any deletion or update, it's going to take a lot more resources. All right, because imagine if you had a table with 20 columns. If you do columnar representation, what does that imply about the number of files? It implies 20. Could be a little bit more, could be a little bit less, but we'll say 20 for this example. And you remove a single record. It means you're dealing with 20 files, right? Is that going to be slower than dealing with one file? Ceteris paribus, of course. It will. Okay, also you have the cost of decompression. All right. So all these things, I think there are going to be very few cases in which this makes sense. With extremely large databases, it could make sense. However, the downside is that the more you split it up, the more processing is needed to compile it together for whatever you're wanting to do with the data. When you get to that point, it probably just makes sense to just straight up not use a relational data model. All right, so just to wrap up, talk about data storage architecture a little bit, talked about organizing files, talked about organization of records in files, talked about data dictionary storage, talked about database buffers, and we talked about columnar-oriented storage. Now, aren't you all glad that SQL, pretty much any implementation you're using, aren't you glad you don't have to mess with this for the most part? That's a good thing, isn't it? All right, that's all I got for today. Go to the career fair if you want. Have a good day.